All right, here we're going to do this. This next one is it's 9.8, and first we're going to find the derivative. Now, these power series, can be differentiated term by term. We're going to if it has a positive radius of convergence, I should add, and this one does. So we can go ahead and differentiate term by term. So we're going to start right in here. Now leave that index off for now. Occasionally, we lose a term depending on the expression in here. But right now, remember you're differentiating with respect to x, so you bring down that power and you lower it by 1. It's a power function, so we're using the power rule. And now you've got this under here. Okay, notice that n cancels itself out. Now, we're still at n equals 1. Okay, now you can double check that. Notice your first term here. You want to make a quick check that you haven't gotten this wrong. This first term, if we were to expand this, we would end up with a x minus 5, and we would have a 5 like that. And the next term would be minus, okay, minus x minus 5 to the second power. That would be over 2 times 5 squared. Now notice, and there'd be the rest of the terms. If you took the derivative of this first term here, you would end up with 1 over 5. And the x would be to the 0 power, so you'd have 1 over 5. The next term, you'd have a minus, and that power would come down and be a 1. The 2's would cancel, and you'd have a 5 squared. Now notice what we have over here. N is 1, we would have n minus 1 would be 0. So we'd have a constant, that'd be the 0 power, so that would be a constant. And then we would just have 5 to the 1. And that's what we have here, 1 over 5. Okay, so you want to make sure if you're going to do your differentiation of this closed form series, make sure that you've got the index right, because occasionally this index will shift depending on the nature of your derivative here. So this may go up 1, it may stay the same. It may drop down to 0, depending on the operation. For differentiation, it usually does not drop down. It usually either skips up a step or stays as it is, depending on the function. So, okay, so here's our series then, without the n. And the question is this series at the first endpoint we talked about, we're testing that. So at a 0 here, we're going to have a minus 5 to the n minus 1, and then you'll have 5 to the n, like so. So this reduces down to, again, remember that negative 1 can be to the n minus 1. That makes that negative 1 to the 2n. Okay, because this becomes a negative 1 to the n minus 1. And then when you add it, those exponents, you get a 2n. So it's just a negative 1 to the 2n. And that leaves a 5 to the n minus 1 and a 5 to the n, like so. So that looks like this. Take one more step. The 5 to the n minus 1, that just gives you 1 over 5. Now, this negative 1 to the 2n is even. If you're raising negative 1 to the 2n, it's always going to be positive 1. Okay, so now look what you have here. You have a series, and this series what happens to it? Does it converge or not? Well, it's constant. You could argue easily enough that the limit does not equal 0, so we have divergence. And remember the name of that test, nth term test. That's what we call it. Okay, so you're not able to add the 0. What about the other number, f prime of 10? Well, that gives you this series, minus 1 to the n plus 1, and a 5 to the n minus 1, all over 5 to the n. And that becomes just a minus 1 to the n plus 1 over the 5. So it just alternates. This is like this other one. It alternates between -1/5 and 1/5. So it's still going to diverge. Okay. It does not by the same test, the nth term test. Nth term test. Okay, so you got to recognize that and state it. Okay, so now next is it's going to be that integral. Let's see. Now, rather than stay with this closed form, I mean, we could, but really the only question is, in fact, we'll do that. Let's just go from here down to here. Let's find the integral of this thing, the integral of f of x. Well, that means we'll do term by term integration on this, and we could do the whole thing at once. In other words, if I start taking the integral of this term in here, of an x minus 5 to the n plus 1, and then an n with an n plus 1 here, with a 5 to the n. So the only real question is, where do I start n? Okay, where do I start n? Do I start it at 1? Well, we suspect we're going to add a term to this. Oh, and by the way, let's not forget our constant. So the only other question is, where do we start the n? Look up here at the original series and notice what would happen if you had integrated term by term. You would have had this. That would have been your first term if you integrated. Come down here. You want a positive first term, so n would have to be, in this case, if you started, you had a 1 there. This first term would be positive. So you would need that n to start off as a 1. Okay. That would guarantee that you begin with n equals 2. Or sorry, with an exponent of a 2 if n were equal to 1. So that would work. Also, notice what happens to the denominator. Let's check that. We'd have a 1 times a 2 and a 5 to the first power. Well, let's see, that's what we have. We have 1 times 2 times 5 to the first. So that works. If you want, you could check the next one, which would end up being an x minus 5 to the third over 3 times 2 times 5 squared. Okay, that's a minus. So down here, if n equals 2, we will have a negative, and we will have an x minus 5 to the third, x minus 5 to the third power. And down here, we'll have a 2 times a 3 times a 5 to the second power. And that's what we have up here. So, and don't forget your constant now. So let's check. This is, I was calling this f of x, like that. And let's check f of 0. Okay, let's check that. Well, in this series, it would be n equals 1. We have a minus 1 to the n plus 1. And then you would have a minus 5 to the n plus 1. And then underneath, we'd have an n with an n plus 1, and a 5 to the n. Okay, so our job is to figure out if this converges or not. Well, we can see it's alternating. We'll take that -1 to the n plus 1 and combine it with this one. We'll have a -1 to the 2n plus 2. And that remaining 5 to the n plus 1 ends up as a 5 because n plus 1 and an n down here. You still have this n as an n plus 1. Okay, so at this point, you realize this is not an alternating series. That -1 to 2n plus 1 is not alternating. It's always the same. It's positive. So we really just have this. Now, you need to do whatever work is necessary to show that this is convergent. Probably the easiest thing would be, I would say that the ratio test, well, limit comparison, compare it to 1 over n squared. Okay, in fact, let's just do that really quick, just for a review. N plus 1. You want to find this limit. Okay. I don't need the bars actually. They're both, I mean, they're both positive terms. So this would be n, whoops. Let's see, n plus 1, and we'd have a 5 n squared underneath. This limit, okay, that's, I want to find this limit. And that limit would be 1 over 5, which is less than 1. Well, okay, I'm doing the limit comparison, so I was thinking about the ratio test, so I take that back. Yeah, let me get rid of that. I don't care about that. I just need to know that this thing is positive and finite. So by the limit comparison test, LCT, we know that both of these theories would do the same thing, and that is they would both converge since this is convergent comparison. So it does converge. And that means that we get to add 0 to the interval. So far, we've got this 0 with 10. Now, the last thing would be to check that 10 and see if we can throw that in. So let's do that on the next page. Okay. Let me do this really quick. Let's see, I've got this. Okay, here. Okay, so here's our function. This is our integral function. And we had that c on there. And by the way, in the last, you might be saying, well, hey, what happened to the c over here? I kind of ignored it. I'm really worried about the series part of the function. When I put an f of 0, there is a c added onto that, but it has no part in the convergence of this series. It has nothing to do with it at this point. Okay, so the c could remain there. You can just ignore it for this purpose in here. Okay, so and again now over here, if you were a stickler for that detail, f of 10, you have -1 to the n plus 1, and then you'd have, let's see, you know what? I've got the wrong function up there. Let me fix that. I've got the, I was using the portion that was already evaluated at 0. So I'm gonna take this and put it in over here. So this is the function that we're working with here. Okay, and a little bit of cleanup here. Okay, so that's the function we're working with. That is f of x. Okay, so f of 10 is going to be this. We'll have a 5 up here to n plus 1, and then down here n plus 1, and 5 to the n. Okay, plus your c. But again, that c is not going to make any difference in terms of our convergence or divergence. Okay, so back in here, one more simplification here. That 5 to the n plus 1 over the 5 to the n just becomes a 5. And now you've got this. And this thing is obviously convergent. In fact, it's absolutely convergent. It would converge even without this negative 1 to the n plus 1. So we can see again, this one you could use the alternating series test on it and show that it does converge. Okay, converges by the AST. So because it's alternating, you would have to cite the AST for that. Okay, so that means in conclusion, we've got the interval of convergence as 0, 10 for f of x, the integral of the original function f of x. Okay, that was long. Hope you made it through.